All right, Chapter 8, Test Preparation. This chapter is on similarity, so we're dealing with similar figures, namely scale models of one another. And so that's what all of these questions are going to be about. There are 6 questions on this test. So without further ado, we're going to jump right in. First problem is from section number 1. This is what you will be given. Section number 1 dealt with dilations. It was this introduction to a fourth transformation, a fourth type of movement in mathematics. And in this one, we're dealing with basically magnifying or minimizing a given figure. So in this first problem on your Chapter 8 test tomorrow, you're going to be given a series of coordinate points. We're given 4 here, perceivably meaning that we're dealing with some 4-sided quadrilateral on the coordinate grid. And in that quadrilateral, we are going to be either magnifying it, making it larger on the coordinate grid, or minimizing it, reducing the size of it on that coordinate grid. And what we learn in this section is that in order to magnify or reduce, we have what's called a constant multiplier, or what we call a scale factor. That term factor referring to multiplication. And in this case, in this problem, we're going to be given some k value. That k value represents that scale factor, that constant multiplier. In this case, it's 1/3 or 1/3. And this is ultimately what's going to change the shape or transform whatever given figure we're dealing with. Now, in the original section 1 notes, in your assignment and stuff, you would have had to graph or plot these points and then plot the image after this dilation that we're going to be performing. But for the sake of tomorrow's test, this is essentially what you're going to get. You're going to be given a series of coordinate points, right? And then you're going to be asked to identify the new image coordinates after a given dilation, a given scale factor. So essentially all we're going to be doing here is multiplying this k value, this scale multiplier, by each of the coordinate points we're given, and just looking for whatever coordinate pops out the other side. Due to the limitations of my distance stuff and graphing, it's just a little bit more foolproof to avoid the graphing aspect here, as much as I would involve this in an actual classroom. But this k value is ultimately going to be what my multiplier is. Again, factor being that key operative word right there, meaning that it's a multiplier. And so essentially, I'm just going to work my way down through each of these given coordinate points, transforming it or dilating it into its new version. So let me start with coordinate point k. Coordinate point k is this -3, 6. I'm going to multiply that by my constant scale factor k. So let me take that -3, 6, which is represented with k, and I'm going to multiply it by my k value. My k value here is 1/3. Now, just a quick note about this. The fact that this is less than 1 here would be 3/3. So the fact that this is less than 1 means that I'm essentially reducing the size of my given original quadrilateral. So it should make it smaller on a coordinate grid. Not that I'm going to have to graph it here. That's just worth noting. If this number had been bigger than 1, again, 3/3 is 1 here, but if it had been bigger than 1, then it would be magnifying it or enlarging it. But I'm going to multiply through this scale factor of 1/3, just distributing throughout with that 1/3. And this is going to create a new image point. Now that image point is still k, so to speak, but we're going to call it k prime. Now this apostrophe, this prime, refers to the fact that it's still k, but this is where it's being moved to. So it's still going to be that same relative corner of whatever this quadrilateral may look like, but this is where it's going to be moved to. It's, in this case, reduced version. And so in order to figure out what coordinate point that is, I'm literally just multiplying this 1/3 by each of these x and y values. 1/3 times -3 gives me -1. 1/3 times 6 gives me 2. There is my image point. Simple enough. All right, I'm going to do the same thing with each of the other ones. So L here is the point 0.6. I'm, again, going to be multiplying by my constant scale factor, again, 1/3. That is going to create a new image point. That new image point in this case would be L prime. It's, again, corresponding image point. And again, just multiplying through by 1/3. 1/3 times 0 stays 0. 1/3 times 6 gives me 2. Moving down the line, point M here, which is 3/3. Is going to be multiplied through by my constant scale factor of k equal 1/3. And converting that into its image point will give me M prime, again, M apostrophe to denote that's where it's moving to. And multiplying 1/3 by 3 gives me 1. Multiplying 1/3 by 3 gives me 1 again. There's M prime. Last one is point N. Point N here is -3, -3. It's okay if it's negatives. Should be aware of that. K is still 1/3. So my resulting image point is now N prime. N apostrophe. And 1/3 times -3 gives me -1. Just be careful of that negative. -3 times that 1/3 gives me -1 again. And there is my series of image points. So had it asked me to graph that, then it would simply be about plotting these points on a coordinate grid, just reading the coordinates as they are written. But in this case, again, for this problem on tomorrow's test, this is essentially all I'm looking for. The conversion from some original point multiplied by its scale factor to give me its image result. You're just going to do that same multiplication. Essentially, this problem just breaks down to multiplying. And you could also consider it like distribution, right? But there's problem number 1 from section number 1 on dilation. All right, problem number 2. Actually, problems numbers 2 and 3 are both going to be referenced in section 3 of our notes. We're going to skip over section 2. Section 2 was on similarity transformation, which is pretty graph heavy. And again, as I said in the previous example, that's why I'm going to avoid it in this, because it's a little difficult to do that over distance. So again, these next 2 problems are going to come from section 3. Section 3 dealt with similar polygons. And the kind of the punchline of this section is that similarity, or scale models of one another, basically broke down into 2 pieces. Piece number 1, that if 2 figures are similar to each other, or zoomed out, zoomed in versions of each other, one thing has to be maintained, and that's the general shape. And that shape is dictated by internal angles. Basically, corresponding angles need to remain congruent. Okay, the way that a shape is maintained, the way that shape keeps the same general look of each figure, is that the angles on the inside will remain congruent. They're going to remain the same. But the second point dealt with the fact that, all right, the shape is going to be the same, but I want the size to be variable. Okay, they don't have to be exact copy and paste versions of the same object. That would be what we call congruence or equality. But similarity instead is I can have a scale model version, and that scale model is given by the constant of proportionality, what we call K. And that's what we talked about in section 1. And so similar polygons kind of emphasizes those 2 main points. Corresponding angles are congruent, and that corresponding side lengths have a constant scale factor that we call K. All right, so for this next part, you are going to be told for problem number 2 that 2 figures are similar to each other. So I'll give you 2 triangles. There's our symbol for similarity. And so you're going to be given 2 figures, and this is pulled directly from our section 3 notes for the record, but you'll be given 2 triangles for your test tomorrow. So triangle RST, and then some other triangle XYZ. I may give them different names tomorrow, just be aware. It's okay. You'll be given 2 similar triangles. And then you'll be told some information about them, namely in this case, side length, 25, 30, and 20, 12, 15, and 18. Okay, so a couple things to point out. These 2 figures, we are told right off the bat that they are similar to each other. So again, those 2 rules apply here. Corresponding angles will be congruent to each other, and corresponding side lengths will be proportional to one another given a constant scale factor K. Now, the fact that I told you all 3 side lengths here, there are a couple different ways I can interpret which pieces correspond to which, because it's a little tricky here because these are not oriented exactly the same. So maybe you're able to eyeball it and kind of figure out which pieces correspond to which, but the default ways that you can do it. First off, just based on their titles, you can always interpret them in the order in which they're written. Namely, first letter has to correspond with first letter, second with second, third with third, working our way down the line. If it was a more complex figure, I would just keep going, but that's how I can associate. So R corresponds with X. These 2 pieces are corresponding, so on and so forth. Or I could look at them from the side perspective of RS is a side right here. That's going to correspond to the first 2 letters in this guy, XY, and just work my way down the line again. Or the more obvious way to do it in this case, because I'm told all of the side lengths, I could simply go like, all right, well, in this triangle, the smallest side is this 20. So that must correspond with the shortest side in this triangle, being the 12 down here. So those two need to correspond. The two next biggest would be these two guys. Those must correspond, and the two longest sides for the respective triangles are those guys. So again, that's just another way you could do it. That will be valuable throughout this problem. All right, so problem number 2 is going to be a 3-parter. And again, this is pulled directly from our section 3 notes. Part A, you're going to be asked to solve K. K, again, represents the constant scale factor. There is some scale factor that changes this triangle into this one. And for the record, that direction matters. We're going to be starting with triangle RST and turning it into triangle XYZ, meaning this guy is what we would call the original triangle, and this one is what we would call the image triangle. Okay, starting from here, turning into that. That direction matters again because that's going to matter with how K is, because here's what I'll also remind you of, that in section 1 and section 2, we determined that K is equal to some image measurement in the numerator over its corresponding original measurement. So that direction matters. It matters which one's the original and which one's the image in this case. Okay? Because had these been swapped, that's actually going to swap the fraction here. So I just had to be careful about that. I'll make sure I point it out on tomorrow's test as well. So in this case, I only need to look for one pair of corresponding sides. For instance, let's focus on the two shortest sides here, right? Either looking at the smallest numbers in both triangles or looking at the first two letters here and the first two letters here, whichever way you do it. But my similarity or proportionality statement would be as follows, that RS over, or sorry, I messed that up already. Again, I have to be careful about which one's the image and which one's the original. So again, being careful with that. Image is actually this triangle. So XY would be my short side there. And then the corresponding piece here would be RS. This is going to represent K, all right? K, my image length over its original length. So now I just plug in the pieces I know. XY here is 12. RS is 20. There's my image over my original length. And if I reduce this fraction, technically this is my scale factor, but if I reduce this fraction, I'll get it down to something a little bit nicer. 4 goes into top and bottom. That's going to become 3 over 5. My scale factor K is 3 over 5. Quick sanity check here. It makes sense that this value is less than 1. 1 here would be 5 over 5. Because if this is where I'm starting and I'm becoming smaller, my K value should be less than 1. Had I messed up which one was the image and which one was the original, this fraction would simply be reversed. It'd be 5 over 3. And that would make sense if I was starting with this guy and magnifying it to this larger one, where I would want that K value to be bigger than 1. But there we go. All right, there's part A. Part B and C are going to refer to basically identifying which pieces correspond to which. Part B is going to tell you to do the following. It's going to say, list all pairs of congruent angles. Another way of saying that is just which angles correspond to which, because they're going to have to be congruent to each other. Because again, angle measurement will help preserve the shape of one triangle to the other. And in this case, I literally could just work my way down the line. First letter with first letter, second with second, third with third. Okay, so angle R is going to correspond and be congruent to angle X. Angle S is going to correspond and be congruent with angle Y. And lastly, angle T is going to correspond and be congruent to angle Z. Just working my way down the line. Now part C is going to be similar, except I'm going to be dealing with side lengths, or what we would call a statement of proportionality. Similar to what we did right here, but we're going to do it with all 3 sides. So statement of proportionality. Proportion, again, refers to the constant scale factor that I have between all 3 sides right here. And so my statement of proportionality, I can, again, just work my way down the line. All right, first 2 letters RS are going to correspond with the first 2 letters XY. Second and third will correspond with second and third. First and third will correspond with first and third. Okay, that would be all 3 sides right there. So I can just work with that. One of those ratios is going to be the same one I did for part A. I just, again, need to be careful about making sure my image is on top in the numerator and my original figure is in the denominator. Original being the larger RST, image being the smaller XYZ. So just starting with what I had in part A, XY over RS. That's going to match the ratio for the next two sides, say YZ, the next second and third letters, to ST, second and third letters. And that's going to match the first and third letters being XZ and RT. Again, I just need to be careful here about which triangle is going to be represented in the numerator, the image where it ended up, the smaller triangle in this case, and in the denominator, my original larger triangle. All three of these ratios have to reduce to the same scale factor K. I happen to know what this value is now because in part A, we reduced that down to 3/5. So whatever those side lengths end up being, all three of them need to reduce down to this 3/5 scale factor ratio. And there's your statement of proportionality. It's expanding on this concept here. I'm just comparing each of the three sides. For the record, in part A, I could have taken any of these other two sides as well and gotten the same result. It's just this is the complete statement. All right, so there's problem number 2, a 3-parter. All right, so this next problem is also from section 3 notes on similar polygons, but in this case, you're going to be actually solving for a missing variable. This one will actually be a little bit faster. That problem number 2 is one of the longer ones on the test. Okay, so in this case, you are going to be told that you have similar triangles again. These ones are going to be DEF. It's going to be similar to triangle MNP. Or you'll be told that two figures are similar to each other. And then you're going to be asked to solve for a given variable. Okay, so in this one, again, this is pulled directly from our section 3 notes. We're given the following figures. Okay, we're given D, E, and F, and we're given a slightly larger M, N, and P. And then we're told some information about the sides. Just what's going to happen here is that one of my sides will involve an unknown, namely EF right here. But we'll know basically everything else, and it's just a matter of like, all right, I need the correct statement of proportionality. So in this case, what I'm going to end up doing is I just need to take my unknown, this EF side here, along with this corresponding piece. I could either, again, refer to the names or simply look for these two happen to be oriented the same exact way. So I can see that this piece here on the left is going to match this piece here on the left. EF is going to match NP. That's also confirmed there. So I know that EF over NP is going to match or be equal to some other pair of sides. And the reason I need to compare it to two other sides is because this one involves an unknown. I need to figure out what this guy equals. So let's just choose this one, DE and MN. So I just have to make sure I'm consistent. Notice that EF and DE are part of the same triangle. So they're going to be in this upper deck right here. And the denominator, its corresponding piece being MN. All right, so this has to maintain the same scale factor, whatever it ends up being. It's just that in this case, I'm going to deal with an unknown that I'm solving for X. So EF, there's my unknown. This one's going to be X. NP, this one right here, ends up being 30. DE, that's another piece I know, that's 15. And MN ends up being 18. So I know both of these. This will end up reducing to something. That value will end up being my K, my scale factor in this case. And whatever this ends up reducing to, it has to be the same. So how do I solve for the variable here? Here, because I have a fraction equaling another fraction, here's where I can use the strategy of cross multiplication. Anytime I have a fraction equaling a fraction. So if I multiply 18 times this X, I get 18X. 30 times the 15, you can confirm it on a calculator, but it comes out to 450. Great, so I have an algebraic phrase at this point. Now it's just solving for my variable as usual, as we've traditionally done in years past. I would combine any like terms, no need to do that here. Everything's just kind of contained already, and then move stuff away from the variable. So in this case, I need to move this 18 to the other side. I'm going to move it by division. So x here will equal 450 divided by 18. You can confirm it on a calculator again, but it comes out to 25 in this case. Again, this is pulled directly from our section 3 notes. So we've successfully identified x. Just to confirm that result, to kind of check our work. 15 over 18, that was a definitive ratio that I was given here, DE and MN. If I were to reduce this, 3 goes into top and bottom. That would reduce to 5 over 6. If I were to plug this 25 back in here, this should also reduce to 5 over 6. And we would see that 5 would go into top and bottom, and I would get it down to that 5 over 6. Confirmed. Same ratio. So those are our problems on similar polygons from section 3. Let's move on. All right, these next two problems are actually going to be referenced in both section 4 and section 5. In sections 4 and 5, we're dealing with this concept of like, okay, well, if I have two similar shapes, how can I show that they're similar in the least amount of information possible? And so the reason why we're going to get two sections referenced for these problems here is that in section 4, we introduced the concept of Aa theorem. Basically, if I can show two angles in one triangle are congruent to two angles in another, then the third one is predetermined by the Triangle Sum Theorem. And so if all three angles in one triangle are congruent to all three angles in another, they have to be similar. In section 5, we talked about Sss Theorem, or if there's a constant rate of proportionality between all three sides, they have to be similar. And then there was Sas Theorem, where if I have two sides proportional to two other sides and their included angle, or the angle that's wedged in between those two sides, is congruent to the other, again, similarity is confirmed. But here's where I'll remind you of these questions. This is actually based on a question that we had in section 5, where we first had to determine if two given triangles were similar. So first thing I need to do is I need to determine if two given triangles are similar. If they are similar, solve for k, k being that constant rate of proportionality, that scale factor. And then I need to determine which of the three theorems split between these two sections, which theorem made it possible. Write that out, made it possible. I'll abbreviate that. There we go. All right, so I'm going to be given triangles, and I'm going to have to determine if they're similar. So it is based on that question, it is possible that they're just simply not similar. Then I'm going to solve for k if they are similar. So if they're not similar, there is no constant k, so I could just stop at that point. And then I need to determine which theorem made it possible for me to reach that conclusion. All right. Again, the three theorems for this last question would be Aa theorem in section 4, Sss or Sas in section 5. All right, so the first one I'm going to give here, this is pulled from section 4. Okay, but we're going to be given two figures. All right, triangle CDE, and then triangle HGK. We need to determine if these two are similar. Now we're going to be given some information in this problem. If you recall from section 4, we were told that these two angles were right angles. So we're dealing with two right triangles. And then we were told a little bit of information about angles here. So we were told that angle C was 26 degrees. And we were told that angle H here is 62 degrees. All right. A couple things to be aware of, again, before I attack a problem like this. Again, if I'm answering these questions. First, I need to kind of determine what's even possible for me to use, because I have three options here based in these sections for how to show that these two triangles are similar, that one's a scale model of the other. It's also possible that they simply are not, but I need to prove what they are. So first off, I want you to notice that I don't have any information about any of the side lengths to either of these triangles. And because of that, that pretty much eliminates section 5 possibilities. In section 5, again, there was Sss theorem, in which case I need all three side lengths to be proportional to all three other side lengths. Well, again, no information there, so I can't do that. And then the other one here was Sas, and again, I run into the same problem. I don't have any side lengths, let alone two of them, right? So all that's left here is section 4, which involves the Aa theorem, in which case I need to show that two angles in one triangle are congruent to two angles in the other. Now, I am given information about two of the angles in both, but they might not necessarily be the same two corresponding angles. So let's start with the more obvious piece here. First off, that angle D is in fact congruent to angle G. Angle D and angle G are both right angles, therefore they're congruent. They're both equal to 90 degrees. So one of the two angles, check. Okay, again, still possible that they are similar, still possible they are not. But in order to be similar at this point, I need at least one other pair of congruent angles. So it's tempting at this point to be like, well, they're not, because 26 doesn't equal 62. And that's true. But the more important thing to ask here is like, all right, well, there are three possible angles in every triangle. These two are already accounted for. So this 26, I need to determine, oh, well, obviously it doesn't equal that 62, but does this angle equal 26 degrees? Or flip side of the same coin, does this angle E equal that 62? In either case, I need to find the third angle of one of the triangles to determine if either of the other two match this 26, or if either of these two match the 62. All right, so in this case, I'm going to use a pretty commonly known theorem, and that's called the Triangle Sum Theorem. And I'll go ahead and deal with this triangle. Let me find angle K. In the Triangle Sum Theorem, in every triangle, no matter which triangle it is, all three internal angles need to add up to the same amount, namely 180 degrees. So algebraically, I could write that measurement of angle G plus measurement of angle H plus measurement of angle K, all three of these angles together has to equal 180 degrees because it's a triangle. Okay, well, I know some of these pieces. I know that angle G, for instance, is 90 degrees because it's a right angle. I know that measurement of angle H is 62 degrees. That was given to me. The one I don't know is angle K. And so solving for that, I would just add up the 90 and the 90 and the 62 and subtract it from 180. So 90 and 62 gives me 152. I need to find out what's left over basically for that third angle, measurement of angle K. In this case, the leftover third angle. So subtracting 152 from 180, I will find out that measurement of angle K in fact equals 28 degrees. And this is important. So this is a determined fact now, that in this triangle, this has to be the third and final angle. This guy here has to be 28 degrees. Why did that matter? Because now referring back to this problem, this 26 degrees now does not match either of those two. I don't even have to bother with solving for angle E at this point. I have one pair of congruent angles, but I do not have a second pair of congruent angles. So my conclusion in this problem would be that these two triangles are not similar. Now, be aware, in tomorrow's test, it is completely possible that had I gone through this math, 26, that could have been 26 as well, right? Not with this combination. But if I had been able to solve and find out, like, okay, that those do match, then they would be similar by the Aa theorem. In this case, they're not similar also by the Aa theorem because there weren't two angles that were similar, or no two angles that were congruent. And because they're not similar, I don't have to bother with finding some scale factor K because they're not similar. There's no constant scale factor K. So that one's done. All right, next problem, problem number 5. Again, we're going to be asked the same thing to determine if two given triangles are similar. If they are, determine their scale factor K, and then which theorem made it possible. But now I'll pull out a different example. All right, so in this one, we'll do this guy. Let's say, I need to give myself space here. So a different diagram. All right, we're given W, X, Y, Z. This example is taken from section 5, by the way. We were told that this was a right angle, and then we're told all the side segment information, 20, 16, 12, 9, and 15. Okay, so same questions apply here. Are these similar? And by are these similar, let me just clarify this. This is triangle XZW. The triangle here on the left, is this similar to triangle YZX, the triangle here on the right? Okay, this is the question. in this problem. I have to distinguish that because technically there is a third triangle. WXY is a major triangle here. But anyway, clarifying these two triangles. So in this case, you'll notice that I'm given very minimal angle information, but I am told everything about the sides. And that's ultimately why I'm going to use the section 5 technique of SSS. So in order to do that, I need to create a statement of proportionality and check to see if I have a constant scale factor K. So let me just work down the line here. That would give me XZ over YZ has to match second and third letters ZW over ZX. And first and third letters XW over YX. Whatever these three are, if they are similar, they will equal some constant scale factor K. If any of them are not equal to the other, they're simply not similar. Okay, so let's go about solving this. I actually know all the information here, so I can just plug stuff in and go for it. So XZ in this case is 12, YZ is 9, ZW here is 16, ZX is 12, XW here is 20, and YX is 15. And so what I'm looking for here is each of these represents some proportionality, some ratio. I just need to reduce it to find out they're the same thing. 3 goes in the top and bottom here. That reduces to 4 over 3. 4 goes in the top and bottom here. That reduces to 4 over 3 again. So far, so good. These two match, but that's not enough information. 5 goes in the top and bottom here. And again, there's 4 over 3. This is now enough information since all three of these equal each other. That implies that there is a constant scale factor K, which for us now means that, yes, these two triangles are similar. And to answer the second part of the question is, what does K equal? Well, convenient enough, we actually just solve for it here. K equaled that constant, in this case, 4 over 3. And which theorem made it possible? Because I had all three sides share that same constant proportionality, I had used the Sss theorem. Now, for the record, I could have used SAS had I done a different strategy in the fact that since this is a right angle, that forces this guy to be a right angle. So I could have used the SAS. I just had to be a little more picky about which sides I use. A little more high maintenance, but not by much. Okay, but there's problem number 5. Again, both 4 and 5 will follow that same standard of first, determine if the triangles are similar. So you have to test it. If they are similar, identify a scale factor K. And then lastly, if they are similar, you're going to determine what theorem proved or disproved that possibility. All right, so for section 6 problem right now, I'm just going to briefly reference what we're going to be seeing. Section 6, this is our last problem on our test. Section 6 was about proportionality theorems. This is basically what you're going to be asked to do. Okay, you're basically going to be asked to solve for X. Now, here's where I want to distinguish what's going to actually happen on your test. The problem you will be given on your test, if you recall, in section 6, there were 3 different proportionality theorems we talked about. There was the triangle proportionality theorem, the 3 parallel lines theorem, and the triangle angle bisector theorem. It'll be one of those that's represented. So let me just briefly sketch all 3 of those scenarios and show you kind of what ratios you'd set up. It is eventually you're going to get some equation of a fraction equaling a fraction. You cross multiply to help solve for the variable. All this stuff, for the record, is in our solution sheet that I highly recommend that you reference in Google Classroom. But let me quickly sketch the 3 possibilities. So this one over here on the left is going to be an example of the triangle proportionality theorem. Okay, where if I had some A, B, C, D, and E. Okay, in this case, the thing that has to be true is that I have parallel bases, as shown by these red arrows right here. And so in this case, the non-parallel sides, the piece over the whole has to equal the piece over the whole. So that would be AE over AD has to equal AB over AC. Okay, there's the triangle proportionality theorem. And again, if there's an unknown in some way, someplace, you would involve cross multiplication for whatever values you plugged in here, and you would use that to solve for X in the traditional method. All right, now the 3 parallel lines theorem. Okay, you're going to be given 3 parallel lines, shocking. And they're going to be crossed by 2 transversals. So now what are transversals? They're just lines that cross the parallel lines. So something like this. So you're going to see this. Again, you're going to be told they're parallel lines. So you'll see these red arrows. Okay. And then, again, you'll be told some information like labeling points. So, for instance, H, G, F, and then C, D, and E. And so, again, piece over the whole, piece over the whole. For instance, HG, this piece down here, use the right color, HG over that whole side length being HF has to equal piece being like CD here over the whole length being CE. Okay, that ratio has to be true. Again, you'll be given an unknown that you use cross multiplication to solve for. And then the last scenario is what we call the triangle angle bisector theorem. And so in this case, you might be given a triangle like this. This was what we had in the margin in our section 6 notes, where you have some angle bisector, where it's going to chop one of these angles in half, and it'll be shown by this little series of arches like that. And so if I label this like, say, V, S, T, and U, what we learned here in this case is that this bisector, this angle bisector, splits this side of the triangle into two pieces, ST and TU. I can make a ratio with those two pieces, these guys, and then I just pair it up. So ST was in the numerator here. ST is going to be paired up with VS in the numerators, and then TU is going to be paired up with this UV down here. So again, you'll be given some unknown, and you'll use that to solve for X using cross multiplication. But those represent the three theorems of proportionality that we had in section 6. I'll help give you some hints tomorrow for tomorrow's test, because I know that was pretty vague there at the end. But that concludes our chapter 8 cheat sheet. I'll go ahead and stop recording right there.